Hi, this is Shane Sylvester. As discussed in my previous video update, my final project for this Introduction to Finite Elements course is a finite element analysis of flow over a step. This is my second video update for this project. My primary focus since the last video update has been the establishment and validation of the first iteration of my finite element model. This preliminary model focuses on flow over a backward-facing step. The model is established via a 2D model on the COMSOL finite element software. I have completed my initial analysis of this model. This initial analysis consisted of a number of steps to reach the current level that I will touch briefly upon in this project update. The first step in the creation of this model was to determine appropriate assumptions. These assumptions have been built upon over the progress that I have made. These include basic assumptions like parameter values, knowing what fluid characteristics will be investigated. The initial model was created with room temperature air, which defines the density and dynamic viscosity, among other flow parameters. Another basic defining assumption has been in the use of Cartesian coordinates. The use of laminar flow was assumed and tested in some model iterations. Boundary layer flow is also assumed with the top portion of the model as a slipping wall. The slipping wall is therefore the free flow velocity, just above the boundary layer. Beyond these assumptions, a number of critical steps have been made to establish the model's first iteration and current level. The steps made in the pursuit of this model were an exploration of the model type. This was the basis of exploration over a variety of model setups and physics-based equations. This led to a sensitivity study conducted over the range of fluid velocities and Reynolds numbers. The exploration over varying Reynolds numbers included exploring over varying flow field size and shape, as well as flow velocities. This carried over several model physics types, including laminar and turbulent flow models, and over varying flow development head lengths. Additional model steps were taken to create stronger graphics with refined streamlines that show the vortex behind the step in the flow. This also required mesh refinement along the boundary layer with the wall and step. The following graphics show images of the current model state. The first image that you see here on your screen now is of the finite element mesh, one example, at the corner and boundary layer along the wall of the backward-facing step. This image shows an exploded view of the flow in the full system, but focused on the backward-facing step, where you can see in the streamlines the vortex created behind the backward-facing step. Validation took place in a number of ways to ensure an accurate model due to the use of 2D Navier-Stokes equations that make model validation difficult. Two primary methods were used for the beginning of this model validation. The first of these was regarding mesh extension studies. This is conducted with the theory that at a certain point, further mesh refinement should not cause significant changes in model results. This was found to be true with slight variations in element shape, although further work may be conducted at this point with varying quadrilateral elements. Second-order elements were found to be crucial in the model accuracy, but allowed for mesh independence from element size. Model results did not vary at second-order elements at normal or finer than normal element size groupings. This also includes adequate coverage of elements over the corner and with boundary layer elements. Boundary layer elements were also found to be mesh independent at a certain size and number. Validation also included comparison of the flow to a one-dimensional maple model solution of the Navier-Stokes equations. This validation included comparing to when both top and bottom walls were true no-slip condition walls, and when the top wall was slipping, as was previously discussed, for the true model. Due to the complexity formed at the step, the model could only be validated away from the step. The plot here shows the one-dimensional solution plotted with a two-dimensional model solution just before the step. The solutions are identical, on top of each other, and difficult to differentiate, even with different size and color lines. Both of these points show great agreement on the model and validity, allowing me to move to the next steps in model development. These next steps were alluded to in the first project update. These include expanding the 2D laminar model for varying step sizes and geometry, possibly seeking an optimized solution in the case of a mandatory step, or a sensitivity study with step size or corner radius. Another step is to conduct model test runs with varying flow material parameters, testing other fluids such as air at different temperatures, thus having different parameters, helium, or even water, which are all common test chamber fluids. The last two steps will be to validate the modeling to a literature review and write the final report to the level